Swayam Prabha. Digital India. Educated India.
Today we are going to look into isotropic and anisotropic materials. Most materials which are used in machine building, they can fall into category of isotropic and anisotropic materials. What is an isotropic materials? Isotropic materials are the ones whose elastic properties are independent of directions. Let us say the modulus of elasticity, modulus of elasticity of such materials are independent of the direction of testing. Think of a block of materials like this. If you consider a specimen oriented in this direction, test it, you will get some modulus of elasticity. If you take another specimen oriented in that direction or in this direction, you will find the same modulus of elasticity. Or even if you test in this direction, it is going to have the same modulus of elasticity. Therefore, the modulus of elasticity is independent of the direction. Similarly, the Poisson's ratio indicates the influence between or interaction between two directions. So, if you consider a situation like this, that you have direction 1 and orthogonal direction 2, the interactions between the strains in these two directions are going to be expressed by Poisson's ratio nu, and this Poisson's ratio between two directions are again independent of the orientations of the direction 1 and 2. Suppose you change it to 1 dash and 2 dash or A and B, you will find the same Poisson's ratio. Now, in such material, you find that the modulus of rigidity, it is related to modulus of elasticity and Poisson's ratio. It is not an independent elastic constant. And another important feature of isotropic material is that you will find that the normal stress applied in any direction, it is not going to induce any deformation or shear strain. Similarly, if you apply shear stress in a plane, it is not going to produce any normal strain. So, the shear stress and normal strain, or normal stress and shear strains, they are uncoupled. Examples of isotropic materials: most of the materials, particularly metallic materials, they are really isotropic materials, except in few cases which we will look into later. Now, let us try to look into what are anisotropic materials. So, in these materials, the elastic properties are direction dependent. So, to say that modulus of elasticity will depend on the direction of testing. So, you can understand now. Similarly, the Poisson's ratio, which gives the effect between two directions or interactions between two directions, this is going to be dependent on the pair of directions that one select. And you find that the modulus of rigidity for such materials are not related to modulus of elasticity and Poisson's ratio. So, unlike the case of isotropic materials, this G is not related to E and nu. It is an independent elastic constant. Another point which is also important for such materials, that the normal stress does produce shear strain, so also shear stress produce normal strain. So, there is coupling effect. Now, examples of anisotropic materials, composites are important examples of anisotropic material. If you consider rolled sheet of steel, it is going to have some modulus of elasticity in the rolling direction, and it will have different modulus of elasticity in the perpendicular directions. So, these rolled steels, they are really anisotropic materials. Now, there are certain timber is another example of anisotropic materials. Now, we will see that these anisotropic materials, there are certain special type of anisotropy, and there are some are typically known as orthotropic materials. So, we would like to look into orthotropic materials. So, there are fixed material directions. For such material, you take that direction anywhere in the bulk of the material, it will have the same modulus, and in some cases they have three such directions, orthogonal directions, which have three independent moduli, and the Poisson's ratio between the two such directions, they are also constant. However, the modulus of rigidity is not related to E and nu, they are independent elastic constants, and for such materials you will find that normal stress does not produce any shear strain, and shear stress does not produce any normal strain. Now, we will look into some examples. First of all, let us see the composite materials. You may not have occasion to come across these materials. Let us talk about them. If you consider some bulk material in the form of plate, and if you reinforce them by fibers located along the matrix, you get, and these fibers are generally made up of stronger material. For example, the matrix could be made up of epoxy, perspex, and the fibers could be glass fibers, nylon, or it could be carbon fibers, and such materials are known as unidirectional fiber composites. They will have strong modulus in the direction of the fiber and lower modulus in the direction perpendicular to the fibers. These materials are really orthotropic material. They have material constants like one modulus in this direction, another modulus in the perpendicular direction. They have one Poisson's ratio constant relating the two directions, and also they have one modulus of rigidity in the plane of the material. So, therefore, there are four independent elastic constants. If this system was isotropic, then you would have had only two material constants. Now, you think of a situation that we have unidirectional fiber composites in different layers of material, and then if we put one over the other and make a combination, that is going to give us what is known as laminated composites, and these laminated composites are going to have an isotropic property. So, you can understand now how laminated composites are made. They are really constituted of orthotropic layers put one over the other. Now, one naturally occurring anisotropic material is timber. If you look into the trunk of a tree, you will find that there are three distinct directions. One is in the longitudinal direction, another in the tangential direction, and the other direction is radial. So, if you take specimen in the longitudinal direction, it will show some modulus. Similarly, if you take the other two directions, they will have two different moduli. And you find that modulus of elasticity in the longitudinal direction is the maximum, and that is why the beams of the timber are made such that they are oriented in the longitudinal directions. Now, in this case you have three independent moduli, then you have the Poisson's ratio effect between the direction L and T, T and R, R and L, these three pairs. So, you will have three constants indicating the influence of the Poisson's ratio. Then you are going to get modulus of rigidity in the plane L, T, T R and R L, three modulus of rigidity. So, therefore, you are going to get three modulus of elasticity, three Poisson's ratio constants and three modulus of rigidity. So, therefore, you will find that for such materials you are going to have 9 independent elastic constants. But in the case of purely anisotropic material, the number of elastic constants would be 21, which we will show you a little later. Now, in the case of timber, you take these three directions anywhere in the whole trunk of the tree, they will show similar properties. So, these are known as actually material symmetry directions. So, that leads to some advantage. Now, let us try to look into the stress strain relations of isotropic and anisotropic materials. In fact, we are going to talk about generalized Hooke's law. Let us consider the direction x, y, z, or in terms of indices 1, 2 and 3, and we would like to have these symbols, that sigma x, sigma y, sigma z, they will be either indicated like this or sigma 1, sigma 2, sigma 3, and shear stresses tau iz, tau zx, tau xy will be indicated as tau 2 3, tau 3 1, tau 1 2. Similarly, we will adopt also the symbols for strains epsilon x, epsilon y, epsilon z as epsilon 1, epsilon 2, epsilon 3 respectively, and the shear strains gamma yz, gamma zx, gamma xy as gamma 2 3, gamma 3 1 and gamma 1 2. Now, if I consider first isotropic material, if we consider the strain in the direction x, let us say that we have all the stresses present here, thereby meaning that we have all the 6 components of stresses. Now, if I consider epsilon x for the material, then under the action of the stress sigma x, I will have strain coming up like sigma x by E. Now, due to sigma y, we will have the Poisson's ratios effect, and therefore, the strain in the x direction will be like this. Similarly, the z stress will give rise to the strain in the x direction given by this one. Similarly, epsilon y is going to be giving the strain sigma y by E in the y direction, and sigma x is going to give contribution nu times sigma x by E. Similarly, we will have z giving contribution nu times sigma z by E, and epsilon z by similar considerations will have nu sigma x by E minus nu sigma y by E minus sigma z by E. So, these are the normal strain, and you see that there is no influence of the shear stresses, and now gamma yz is going to be tau yz by g. G is modulus of rigidity, and you will see that G is nothing but E by 2 into 1 plus nu. Similarly, gamma Zx is going to be gamma tau Zx by G, and gamma xy is nothing but tau xy by G. So, these are the 6 stress strain relations. This is nothing but generalized Hooke's law, and if we write this thing in a matrix form, it looks all these relationship, it can be written in a compact form like this, that the strains are related to the stresses by this matrix, and these constants are 0. So, also these constants are 0, and all the rigidity moduli are coming in the diagonal. And you see here that this matrix, which is known as compliance matrix. So, this matrix is known as compliance matrix. It is a matrix of dimension 6 by 6. It connects the 6 strains to 6 stresses, and it is a symmetric matrix. Now, if we consider the material to be anisotropic, then we will have difference. So, we will now consider, let us say we will consider material orthotropic. Then in that case, we will find that if we now consider the 6 stresses to be indicated like this, then all these 6 stresses, if I now consider together, then strain in the one direction or x direction is going to be nothing but sigma 1 by E minus nu sigma 2 into nu 2 1 by E2. So, the strain in the direction 2 is sigma 2 by E2, and its Poisson's ratio effect is expressed by nu to 1, and this is going to be negative. So, therefore, nu to 1 by E2. Similarly, this sigma 3 is going to give contribution to one direction like this. So, you can go on writing in the direction 2, we will have strain due to sigma 2 is sigma 2 by E2, and strain due to sigma 1, it is sigma 1 by E1 multiplied by nu 1 2. You see that this is nu 2 1, this is nu 1 2. Similarly, this sigma 3 stress is going to give strain in the direction 2 given by sigma 3 by E3 into nu 3 2, and it is negative. So, if that strain in the direction 3 is tensile, we are going to have contraction in the direction 2. Similarly, we can write this epsilon 2 also considering all the 3 stresses, and they are going to have constants like minus nu 1 3 by E1 minus nu 2 3 by E2 1 by E3, and then this shear strain gamma 2 3 is going to be given by tau 2 3 by G 2 3, where G 2 3 is the modulus of rigidity in the plane 2 3. Similarly, the next strain is going to be given by tau 3 1 by G 3 1, and gamma 1 2 is equal to tau 1 2 by G 1 2. So, you see here we have 3 moduli of rigidity, then we have 3 we have 3 moduli of elasticity, and then we have 3 moduli of rigidity, and now you will find that this ratio nu 2 1 by E2 is equal to nu 1 2 by E1. So, therefore, in effect we have only one elastic constant. Similarly, this ratio nu 3 1 by E3 is equal to nu 1 3 by E1. So, therefore, again another elastic constant, and this ratio is again same as this one. So, we have 3 Poisson's ratio related constants. So, therefore, these are the equalities, and therefore, we have 3 Poisson's ratio parameters. In total, we have 9 parameters. Again, you see this matrix is symmetric, and therefore, this is the relationship for orthotropic material. Now, if you consider purely anisotropy, then in that case you will find that the relationship is going to be a little different. Now, first of all, if you just concentrate on this part, you have the 6 strains and you have the 6 stresses. Now, the effect of the stresses will be obtainable by considering epsilon 1 equal to C11 into sigma 1 C12 into sigma 2 C13 into sigma 3 C14 into tau 23 C15 into tau 31 and C16 into tau 12. So that is how you get the influence of all these 6 components in the direction 1. Note that here this C14, C15, C16 constants are not 0, and therefore you find that the shear stresses are going to contribute to the normal strains. So you can write the expression for all the 6 strains, and in this there are, it is a 6 by 6 matrix. So this compliance matrix or tensor is a 6 by 6 matrix, but then it is a symmetric tensor, thereby meaning that the 15 terms above the diagonal and 15 terms below the diagonal, they are equal, and therefore you have 15 off diagonal terms plus these 6 diagonal terms, total 21 constants. So therefore there are 21 independent elastic constants, 21 independent So purely anisotropic material would have 21 independent constants. Sometimes this form can be simply written in this form by using the tensor notation epsilon I equal to Cij into sigma j, wherein I is varying from 1 to 6, j is varying from 1 to 6. But in general we can write this in this form, that this is the strain tensor and this is nothing but compliance tensor into the stress tensor. So therefore this is the generalized Hooke's law for anisotropic material. Now you must be interested in knowing some idea about the order of magnitude of the properties of the materials which are anisotropic. So let us consider one composite unidirectional fiber composite which is made up of epoxy matrix and glass fibers. Then in that case you find that if you test the material in the fiber direction, then you have modulus of elasticity as 40 GPa, and if you test it in the direction perpendicular, then the modulus of elasticity is 8.3 GPa, and the modulus of rigidity in the plane is nothing but 4.1 GPa, and then the Poisson's ratio constant nu 1 2 is 0.26, and you can find out nu to 1 by considering this equality. So therefore you see there are 4 constants. Now if the reinforcement is done by carbon fibers, then you find that the modulus in the direction of the fiber is very high, 200 GPa, and modulus in the perpendicular direction is 7, and the modulus of rigidity in the plane is 5 GPa, and nu 1 2 is 0.26. And in the case of timber, so if you consider timber, in the case of timber in the longitudinal direction, that means in the direction of the trunk, you have 16.3 GPa, in the direction radial it is 0.57 GPa, and in the direction 1 2, that means longitudinal radial, the modulus of rigidity is 0.68 GPa, and nu to 1 is 0.0178, that is the Poisson's ratio constant. You will find generally this modulus of elasticity in the tangential direction very close to this value. So therefore you see the order of magnitude, there is a ratio of about 30. Now compare this with the magnitude of steel, which is an isotropic material. The modulus of elasticity is 200 GPa and the Poisson's ratio 0.2. Now I must mention that you can have composite material made up of metal matrix and some other metal as reinforcement. We make now titanium aluminum composite, wherein the matrix is of aluminum and the fibers are of titanium. This gives very good strength, and that is why they are used for high strength applications. And these carbon composites, they can be also you can have matrix of carbon and the fibers of carbon. That is why they are known as carbon composites, and these materials are very high temperature resistant, and therefore they are made and they are made use of in the making of the nose of the re-entry vehicles. The vehicles which go for space exploration, while they are entering into the atmosphere, there is very high temperature which is as high as 3000 degrees centigrade. To stand this high temperature, they make use of carbon-carbon composites. Now, I would like to consider the stress strain relations wherein you have both thermal and mechanical loading. So, therefore, we will now consider thermomechanical stress strain relations. You see that in most power plants, in the chemical plants, in the boilers or turbines, you find that the components are going to operate at high temperature. They are not only subjected to mechanical loading, they are also subjected to varying temperature, and which are very high order of, which are also having high magnitude. So, in the presence of both temperature field in the component and also mechanical loading, you are going to have both thermal and mechanical deformation or deformation due to both mechanical loading and thermal loading. So, we would like to consider how these calculations can be done. In order to do that, we must have relationship between stress and mechanical strain and also temperature. Now, consider the simple case. You take the example of a simple rod, and if you try to increase the temperature of this rod, it is going to expand. If it will go on expanding depending on the thermal expansion, and if this expansion is prevented, then we are going to get some stresses developed in the component which is going to be compressive in nature. But if we allow the free expansion of the component to take place, then we are not going to have any stress developed in it. Now, let us try to see this little more elaborately. Consider one component of uniform cross section. It is held like this. Let us consider that its length is L, its modulus of elasticity, material has modulus of elasticity E, the cross section is A, and let us consider that the thermal coefficient of expansion for this material is alpha, and we now raise the temperature of this material above the room temperature by T, and also this material is subjected to some mechanical loading, due to which there is a stress of magnitude, let us say sigma x. So, let us consider that this is oriented in the direction x. Now, under the action of the mechanical loading, it will have strain, and that strain is nothing but sigma x by E. Now, under the action of the temperature field, it is going to have expansion of magnitude L into alpha into T. Now, if I want to calculate the strain, then the change in length is L alpha T, original length is L, therefore, the strain is nothing but L alpha T divided by L, therefore, it is alpha T. So, therefore, the total strain you are going to get, or the deformation you are going to get, due to part of that is due to thermal. So, let us say this is the expansion due to thermal expansion, and this the expansion further up is due to the mechanical loading. So, therefore, we have strain due to thermal and strain due to mechanical loading. So, therefore, if I want to calculate the total strain epsilon, it is nothing but epsilon mechanical plus epsilon thermal. So, now I can write the value. Mechanical strain is nothing but sigma x by E, and this thermal strain is nothing but alpha into T. So, therefore, the relation, if we would like to write this strain in the x direction, total strain in the x direction epsilon x is equal to sigma x by E plus alpha into T. So, you find that this is the relationship between the strain, stress and temperature. Let us see that we have a case wherein epsilon x equal to 0. So, the total strain equal to 0, then you find that sigma x is equal to minus E alpha T. Therefore, it means that if the component is not allowed to, what I mean is that that if I consider this component and if I increase its temperature by T and we do not allow this to expand, then in that case it is going to develop a stress of magnitude E alpha T, which is compressive in nature. So, therefore, this is the magnitude of the strain when there is no, this is the magnitude of the stress when there is no strain. Now, consider the other extreme. Suppose we now say that epsilon x is equal to alpha T, then in that case sigma x is equal to 0. What it means here, that if you now consider the same component, and now let us say that this is originally here. Now, if I consider it to have expansion, free expansion up to this much, and that means we are not constraining the free expansion, then in that case stress will be equal to 0. So, therefore, you see that whenever there is constraint on the thermal expansion, you are going to have stress in the material, and this stress, therefore, the thermal stress, you will find that it is going to lie all the time in one dimension in the range 0 to minus E alpha T. So, this is really the picture in the case of one dimension. Now, let us try to consider the case in two dimension. So, if we now consider an element of a component in two dimension, let us say that this is two dimensional plane stress condition. So, in the case of two dimensional plane stress, let us try to assume that the stresses on the element are sigma x, sigma y, and the shear stress is tau xy, and at the same time let us also assume that the temperature of the body is raised by T above the ambience. Now, the material properties we will try to make use of E alpha, and thickness is equal to T. Let us consider that this height is equal to dy and this height equal to dx. This loading I can split into two parts. Let us consider that we have, first is let us say that this is the shear loading only, and then we can also consider that there is mechanical loading. So, this is sigma x, sigma y, this is tau xy. So, this is the mechanical constituent of the loading, and then we can also consider that there is thermal effect. So, this thermal effect we can consider it to be again separate. So, therefore, in this case we have rise in temperature by T. So, this problem can be now considered to be made up of 3. Now, in this case you can calculate the strains in both x and y direction, and if the material is isotropic you will get only the normal stresses producing normal strain, there is no shear strain produced by them, and this is going to produce only the shear strain and it will not produce any normal strain, and temperature rise is going to produce strains which is going to be increase in dimensions of the body both in x and y direction. So, therefore, in this case the size of the body is going to increase both in x and y direction, and that increase in dimensions will depend on the magnitude of dx and dy. Note that this thermal rise or temperature rise is not going to give rise to any distortion of the body. So, this is a very important point, that in the case of temperature rise you will find that the form of the body or the shape of the body is not going to undergo any change. So, if you had two orthogonal directions initially, they will remain orthogonal and there is no shear strain produced. So, we can now calculate the strains under the action of all these loadings very easily. So, we will now calculate the strain due to the mechanical part and also thermal part. Before I go into considering the mechanical part, look at the thermal. See, the thermal, if this side is equal to dx, under the action of temperature rise, this is going to expand by dx into alpha into T, and therefore, this strain is going to be dx alpha T divided by dx, therefore, it is alpha T. So, therefore, the strain in this direction, this strain is going to be of magnitude equal to alpha T. So, if you would like to consider epsilon x t is equal to alpha T. Similarly, if you consider this direction, the height is dy, under the action of temperature rise it is going to expand by dy into alpha into T, and therefore, strain is going to be dy alpha T divided by dy. Again, this strain in this direction, it is also going to be of magnitude equal to alpha T. So, therefore, the strain in the two orthogonal directions are going to be alpha T and alpha T. And due to this stress, due to these two stresses in the x and y direction, we are going to get strain in the x direction to be given by sigma x by E minus nu, we will have of course the Poisson's ratio constant nu. So, nu times sigma y by E. So, therefore, I can now write that the total strain epsilon x is equal to epsilon x mechanical plus epsilon x thermal, and now epsilon x mechanical is nothing but sigma x by E, which is due to sigma x, and due to sigma y we are going to get nu times sigma y by E, and shear stress is not going to produce any normal strain. So, therefore, we have no contribution, plus we are going to get this thermal strain which is of magnitude equal to alpha T. So, therefore, this is alpha T. Similarly, epsilon y is equal to epsilon y mechanical plus epsilon y thermal, So, this is going to be again sigma y by E minus nu times sigma x by E, and the mechanical strain is going to be, you have already seen here, this is equal to alpha t. So, therefore, this is alpha t. Now, the shear strain gamma xy, again we will have gamma xy due to mechanical loading, gamma xy due to thermal loading. The strain due to mechanical loading is straightaway given by tau xy by g, and this part is equal to 0. So, please note this, that under the action of the temperature rise, you are not going to have any shear deformation. That is why you see that when you heat a rectangular plate, it will remain rectangular. If you heat a circular plate, it will remain circular. So, therefore, two initially orthogonal directions will remain orthogonal even after deformation. So, this is the stress strain temperature relationship in the case of plane stress, and we can write now this thing in the form epsilon x minus alpha t epsilon y minus alpha t and gamma xy is equal to 1 by E minus nu by E 0 minus nu by E 1 by E 0 0 0 1 by G, I am sorry, this multiplied by, we have sigma x, sigma y, tau xy. So, this is the strain, temperature and stress relation. You can see that the elastic constants are involved here, nu and E and G, and since G is equal to E by 2 into 1 plus nu, we can invert this relationship and once we invert this relationship, we get a form like this. Sigma x, sigma y is equal to E by 1 minus nu square 1 nu 0 0 nu 0 0 1 minus nu by 2 multiplied by epsilon x minus alpha t epsilon y minus alpha t into, and then last term is gamma xy. So, therefore, this gives you the relationship between the stress and strain and temperature. So, this is the relationship for plane stress. You can extend this relationship to 3 dimensions very easily. So, if you consider 3 dimensions, we will have all the components of stresses sigma x, sigma y, sigma z, and then we will have tau yz, tau zx and tau xy, and then we are also going to get thermal field which is characterized by temperature rise T, and if you assume the material constants again to be E, alpha, Poisson's ratio nu, then we can now write that the strain in the x direction is going to be strain due to mechanical loading plus the strain in the x direction due to temperature. Now, if I consider the material to be isotropic, then in that case under the action of the three normal stresses we are going to get strain to be given by epsilon x by E minus nu times sigma y by E minus nu times sigma z by E, and the thermal strain is going to be alpha T. So, you can write the expression for sigma y, sigma z along similar lines. So, I will just write for you sigma epsilon y. So, epsilon y is equal to sigma y by E nu times sigma x by E minus nu times sigma z by E, and the thermal strain will be alpha T. So, you can write very easily epsilon z. So, I will not write that. So, please fill up. Now, if we consider the shear strain gamma yz, that is going to be nothing but tau yz by g, and the thermal strain will be 0. So, therefore, the shear strain is only due to the mechanical loading, and you can write now gamma zx along similar line zx by g, and of course, you can also write gamma xy to be given by tau xy by g. So, these are the 6 relations involving mechanical loading and thermal loading. Now, if you try to invert this relation, then you will get the connection between the stresses on one hand and the strain and the temperature on the other. So, therefore, if you invert this relationship, it is going to give you like this: the stresses sigma x, sigma y, sigma z, tau yz, tau zx, and tau xy. So, these are the 6 stresses, and then we will get the constants like this. It is 1 minus nu, 0, 0, 0, nu 1 minus nu, 0, 0, 0, nu 1 minus nu, 0, 0, 0, one minus 2 nu by 2, 0, 0, 0, 0, 0, 0, 1 minus 2 nu by 2, 0, 0, 0, 0, 0, 1 minus 2 nu by 2. Then we have the common multiplier E by one plus nu into 1 minus 2 nu multiplied by epsilon x minus alpha t, epsilon y minus alpha t, epsilon z minus alpha t. and this is gamma yz, gamma zx, gamma xy. So, this is epsilon x minus alpha t, epsilon y minus alpha t, epsilon z minus alpha t, gamma yz, gamma zx, gamma xy. So, therefore, this is the strain matrix. So, again it is a 6 by 6 matrix, it is symmetric matrix, and this matrix is known as stiffness matrix. Now, you should be able to consider some derivations with whatever we have talked so far. Think of the problems like deriving, of course, these relations in 3 dimensions. Just now I have derived for you. Now, this is something which you must consider. Write the relations involving sigma, epsilon and temperature under plane strain condition. So, this is something you must derive, and that will make all the derivations clear for. Then third example which you can consider, solve problems related to determination of principal stresses and strains from L.S. Srinath, Advanced Strength of Materials. It is published by Tata McGraw-Hill, 2nd edition in 2003. So, this second problem I would like you to think over. So, in this case the picture is like this. You have a component so let us say the directions are x, y, and then we have z direction. So, you have the stresses acting in the x direction, sigma x, sigma y acting in the y direction, then you have shear stresses acting, these are in plane shear stresses. So, let us simply represent by tau xy, and at the same time we are going to have some stress acting in the z direction. So, therefore, we have sigma z stress also acting on the body. On top of this, there is a temperature rise by T. So, the material constants E, alpha, nu, you can find out the strain in the x direction due to mechanical, it will be due to normal stresses sigma x, sigma y and sigma z, and the thermal strain is going to be simply alpha into T. Similarly, in the y direction you are going to get strains due to all the 3 components, and in the z direction you are also going to get similar picture. So, epsilon z is now going to be sigma z by E minus nu times sigma x plus sigma y by E, plus the thermal strain is going to be alpha t. So, therefore, epsilon z is due to mechanical is this much and thermal. Now, since we are considering plane strain condition, there is no expansion in the z direction. So, therefore, epsilon z equal to 0 for plane strain. Therefore, you find that sigma z is equal to nu times sigma x plus sigma y minus E alpha t. So, therefore, in this case you get that sigma z is to be dependent on both the normal stresses sigma x and sigma y and also the temperature rise and modulus of velocity, thermal coefficient of expansion. So, you can now write the expression for sigma x, sigma y in terms of only sigma x and sigma y eliminating sigma z. Thereby, you are going to get relationship involving sigma x, sigma y and tau xy on one hand, and on the other side you are going to get epsilon x, epsilon y and gamma xy plus the temperature. So, you are going to also get temperature. So, therefore, you will find that these stresses are now going to be related to the strains and temperature. So, that will be the relationship which you are to derive, and this relation finally it will turn out to be that sigma x, sigma y, tau xy is equal to E by 1 plus nu into 1 minus 2 nu into 1 minus nu, nu 0, nu 1 minus nu 0, 0, 0, 1 minus 2 nu by 2, that is the material constant, and on the other side you are going to get epsilon x minus one plus nu into alpha t, epsilon y 1 plus nu into alpha t and gamma xy. So, therefore, this is what is going to be the relationship. So, I am sorry. So, this please note it carefully that this is going to be epsilon x minus 1 plus nu into alpha t, epsilon y minus 1 plus nu into alpha t, gamma xy. So, this is the relationship. So, your answer is going to be in this form. Finally, the plane strain relationship will look like this.